Chapter 7, Section 1, Graphing Systems of Equations. Let's get into it. So, a set of two or more equations with the same variables is called a system of equations. So we're going to look at it a lot today where we've got two equations and we're going to be using them together to be able to solve the system. It's called a system. An ordered pair that is a solution of both equations is a solution of the system. So an ordered pair can be a solution to one equation, but not the other. That means that it's not a solution to my system as a whole. It's got to be a solution to both equations to be a solution for the whole system. Okay? A system of two linear equations can have one solution, an infinite number of solutions, or no solution. And we'll look at all of those. I would write these 4 bullet points down at least, if you're going to write anything down on this page. Okay? A system of equations is consistent if it has at least one ordered pair that satisfies both equations. If it has at least one ordered pair that satisfies both equations, it's considered consistent. If a consistent system of equations has exactly one solution, it is said to be independent. The graphs intersect at just one point, one ordered pair. If a consistent system of equations has an infinite number of solutions, it is dependent. The graphs are the same line. Essentially, they're intersecting at every single point. This means that there are unlimited solutions that satisfy both equations. A system of equations is inconsistent if it has no ordered pair that satisfies both equations. The graphs are parallel. Parallel lines do not intersect, correct? So if you're looking for the point of intersection, but they don't intersect, we don't have a solution. There's no ordered pair that satisfies both equations. Any questions about any of this information here? I'll give you a little bit more time to write down. Okay, let's move on. Use the graph to determine the number of solutions the system has. Then state whether the system of equations is consistent or inconsistent, and if it's independent or dependent. Okay? So, what did we learn about on the previous slide about systems of equations? How do I know how many solutions there are?
Exactly one solution is said to be independent.
How do I know if it has one solution though?
If it has exactly one
at one
solution.
point.
The graphs intersect at one point. Okay? If there's an infinite number of solutions, the graphs are the same line, right? And then if there is no ordered pair, aka no solution, the graphs are parallel. Okay? So, do these lines intersect at one point? Are they the same line or are they parallel?
They intersect.
At one point, right? Right here. There's their only point of intersection where they cross each other, right? Everyone okay understanding that?
Yes, sir.
If they were the same line, there would be an infinite number of solutions. If they were parallel, there would be no solution. Does everyone understand that if they intersect at one point, they just have one solution?
Yes, sir.
Okay? So, determine the number of solutions the system has. That'll be our first answer. One solution. Because they intersect at one point, this is the only ordered pair that's going to satisfy both equations. Okay? It's going to make both equations true. Okay. I answered the first question it wants us to do. Now it wants me to state whether the system of equations is consistent or inconsistent, and if it is independent or dependent. How do I know if an equation or the system of equations is consistent or inconsistent?
You have an infinite number of solutions.
If it has one ordered pair,
At least 1,
least
right?
For both?
So it could be 1 or infinitely many.
Right. And then no ordered pairs?
Yeah, inconsistent system has no ordered pair that satisfies both equations. So we said it has one solution, right? So would this be consistent or inconsistent?
Consistent.
Consistent because it has at least one ordered pair that satisfies both equations.
Oh.
Are we okay understanding that? Any questions about that? And then how do I tell if it is independent or dependent?
Say that one more time.
How do I tell if it's independent or dependent?
It has exactly one solution, independent.
Yep.
Infinite number of solutions.
Yeah. One solution, independent, infinitely many, dependent. How many solutions do we have on example 1? One, exactly one. So is it independent or dependent?
Independent.
Independent. If I get a system that is inconsistent, is it going to be independent or dependent?
No.
No. Independent dependence only for consistent systems, not inconsistent. Okay? Have I answered everything they want?
Yep.
Yes, I have. Determine the number of solutions. One solution. State whether the system is consistent or inconsistent. Consistent. And if it is independent or dependent. Independent. Okay? We're okay doing that. Can I move on to the next example?
Yes, sir.
Okay. Same type of process here. Use the graph to determine the number of solutions the system has. Then state whether the system of equations is consistent or inconsistent, and if it is independent or dependent. So what do you notice about these lines?
Parallel.
They're parallel. So how many solutions would you say that this system has?
Done.
None. In order for there to be a solution or infinitely many solutions, the lines would have to be intersecting at some point. Do parallel lines ever intersect? Nope, they're never going to cross. If I'm looking for the point of intersection, but they don't intersect, I've got no solution. Are we okay with that?
Yep.
Anytime you have a system of equations and they're parallel, you got no solution. Okay? We good with that? Okay, state whether the system of equations is consistent or inconsistent. Which one is it? Inconsistent because it has no ordered pair that will satisfy both equations. The graphs are parallel. It is inconsistent. If it's inconsistent, can it be independent or dependent?
No.
Nope. So I'll just leave it at that. Questions, comments, concerns on examples 1 or 2?
No.
Okay. Example 3. Determine the number of solutions the system has, then state whether the system of equations is consistent or inconsistent, and if it is independent or dependent. What do you notice about this example compared to the other two?
There's no graph.
There's no graph. We don't know what the graphs look like, do we?
No.
No, unless we were to graph it ourselves. There actually is a way to do this without graphing it ourselves, and that is to look at the slopes and the y-intercepts. What do we know about slopes of parallel lines?
They are the same.
They're always the same, right? Parallel lines always have the same slope. Would parallel lines have the same y-intercept as well?
No.
Why not?
Well, they can.
If they had the same slope and the same y-intercept, what would they be?
They would be,
Not what I'm looking for. They would be the same line, right? So the same line is not going to be parallel to itself because it's the same line, right? It would just be the same line. It would have infinitely many solutions because it's intersecting at every single point. Okay? So let's analyze these two equations here. We probably want them to be in slope-intercept form to be able to identify the slope and the y-intercept easily. So for this first equation, y equals 6x plus 10, what is my slope?
6,
6. What's my y-intercept?
10.
10. Second equation, what's my my slope?
6.
6. What's my y-intercept?
4.
4. What do we notice about their slopes?
Same slope.
Same slope. What do we notice about their y-intercepts?
Different.
Different. So would you say that these two lines are the same or are they parallel? Parallel. Because they have the same slope but different y-intercepts. We okay with that? So, we've determined that they are parallel lines. What do we say about parallel lines? How many solutions do they have?
None.
None. So this would be no solution. Consistent or inconsistent? Inconsistent. Can inconsistent be dependent or independent?
No.
No. So we'll leave it at that. Did we see how we processed through that? Okay. Let's say we did. Let's say we got same slope, same y-intercept. What type of lines were these? If they have the same slope and same y-intercept. Same exact line. How many solutions would those have? Infinitely many. That would be consistent, and that would be dependent. If we got different slopes, are these going to ever be parallel? If they have different slopes? No. They're also not going to be the same line if they have different slopes. So they're going to intersect sometime at one point, meaning how many solutions do they have? One. So it would be consistent and independent. Okay? Any questions about examples 1 through 3? I believe example 4 is very similar to the one we just did, except what do you notice about the equations? Yeah, we have to solve for y. They are not in slope-intercept form. So I've got to go ahead and get them to slope-intercept form, in order to easily identify the slope and the y-intercept. Okay? So, 4y minus 6x equals 16. What would be my first step to get y by itself?
Plus 6.
Add 6x. Can I combine 16 plus 6x? Nope. So I'll write it out as 6x plus 16. How would I get y by itself? Divide by 4. Divide everything by 4. Will 6 over 4 give me a whole number? Nope. What are 6 and 4 both divisible by, though? 2. 6 divided by 2? 3. 4 divided by 2? 2. 16 divided by 4? 4. So there's my first equation, solved for slope-intercept form. What is my slope of that equation? 3 over 2. And my y-intercept? 4. Okay, we'll use that here in a second after we solve our other equation. Questions on what I've done up to this point? (9x minus 6y equals negative 24). It's my first step to get y by itself. Subtract 9x from both sides. Once again, these are not like terms, so I can't combine them. So I just write it out. How would I get y by itself?
Divide negative 6.
Divide everything by negative 6. Will negative 9 divided by negative 6 give me a whole number?
No.
Nope. Can I simplify 9 over 6? 9 and 6 are both divisible by
3.
3. And negative divided by negative gives me a
Positive.
positive. 9 divided by 3? 3. 6 divided by 3? Negative 24 divided by negative 6? Positive 4. There's this new equation solved for slope-intercept form. What's my slope here? 3 over 2. Y-intercept? 4. How do these slopes of these two lines compare? Same slope. How do the y-intercepts compare?
Same,
Same y-intercept. What is true about these lines?
same line.
Same exact line, because they have the same slopes, same y-intercepts. Okay? So it's the same line, just one line graphed on top of the other. How many solutions do we have if they're the same line? Graphs are the same line. How many solutions do we have?
Infinite.
Infinite number of solutions. We okay with that? So, is there at least one ordered pair that satisfies both equations here? If I have an infinite number of solutions, then yeah, I for sure do. I've got an infinite number of ordered pairs that satisfies both equations. So do I have at least one?
Yes.
Yeah, so that means it's what? Consistent or inconsistent? Consistent. Now that it's consistent, I can now tell if it's independent or dependent. If it's the same line and I have an infinite number of solutions, what is it? Dependent. There's my answers. We okay with all of that? If you get different slopes, you're going to have one solution because they're going to intersect at some point. Okay? Questions on this example?
Nope.
How we feeling?
Good.
Good. Essentially, this first part of the lesson is having those definitions in front of you of what consistent, inconsistent, dependent, independent means, and being able to tell if there's one, no, or infinitely many solutions. Okay? You don't necessarily have to write all this down. Just pay attention to what it's saying as I'm reading it out loud to you guys. You can solve a system of equations by graphing each equation carefully on the same coordinate plane. Every point that lies on the line of one equation represents a solution of that equation. Does everyone agree that every ordered pair on this blue line, if I plugged it into this equation, it would make it true? That's what a line means, the graph of an equation. That's what it means. Every ordered pair is a solution to that equation. Okay? Does that make sense? Same thing for this orange line. Every ordered pair on this orange line is a solution to this equation. Everyone okay with that? Similarly, every point on the line of the second equation, like I just said, in a system represents a solution of that equation. Therefore, the solution of a system of equations is the point at which the graphs intersect. So if every ordered pair on this line is a solution of that equation, every ordered pair on this line is a solution of that equation, where they intersect has to be true for both of them because that point is on both lines. Does that make sense? So that's why we look for the point of intersection for the solution of a system of equations. So for example, the solution of this system is this ordered pair, -1, 3. That is the point at which the graphs intersect. Since the point of intersection lies on both lines, the ordered pair satisfies each equation in the system. And I could check that if I wanted to. Plug in 3 for your y's. Plug in -1 for your x's and work down both sides of each equation. If you get a true statement, that means it is a solution. So, overall, big picture, to solve a system of equations by graphing, graph the two lines. Wherever they intersect, that's your solution. You guys got that? Point of intersection is the solution. Can I move on?
Yep.
Okay. Got the big idea? Okay. Example 5 here. Graph the system and determine the number of solutions that it has. If it has one solution, determine its coordinates. Essentially, tell what ordered pair is the solution. Okay? So, do you guys remember how to graph? Using slope-intercept form. We got to identify the slope and the y-intercept. graph the y-intercept first. Use your slope to get more points. So first equation, y equals negative 2x plus 14. First off, is that slope-intercept form?
Yeah.
Yeah. So I can easily identify it right off the bat. What's my slope? Negative 2. For graphing purposes, what would that be as a fraction?
2/1.
Negative 2 over 1. For the first equation, what is my y-intercept? 14. What is a y-intercept? It's where my graph crosses the y-axis. Very good. So, our y-intercept's 14. Find the y-axis. Go up 14. Put your point on 14. That's our starting point for all of our other points. Okay? Now, slope, rise over run, is negative 2 over positive 1. How many directions and which 2 units am I going using negative 2 over 1? Down 2. What do we say? Right 1. Very good. Be careful. If you are given a graph, always check what your axes are going up by each time. What is my y-axis increasing by each time? 2. So if I go down 1 tick mark, that's down 2 units. Does that make sense?
Yep.
What's my x-axis increasing by each time? Also 2. So in order to go right 1, I've got to just go halfway. Does that make sense? So, down 2, right 1. Down 2, right 1. Down 2, right 1. Down 2, right 1. We okay with how I got all my ordered pairs here?
Yep.
Connect your points with a line. Put your arrows on your line. There's nothing constricting me to just stay in one quadrant or anything like that. I don't just need all positive values. We're just dealing with an equation, so it is going to extend forever and ever and ever. There's my first graph. But in order to solve by graphing, I need to carefully graph each point on the same, or each graph on the same coordinate plane. So I've got to graph my second line as well. What's my slope here? 3 over 5. What's my y-intercept here? 1. Once again, graph your y-intercept first. Go up 1. That'll be halfway between 0 and 2. Positive 3 over positive 5. Which 2 directions, how many units am I going?
Up 3, right 5.
Up 3, right 5. 1, 2, 3. 1, 2, 3, 4, 5. So this is my next point. 1, 2, 3. 1, 2, 3, 4, 5. Everyone okay with that? 1, 2, 3. 1, 2, 3, 4, 5. So it'll be right here. What other 2 directions can I go for this one? Down 3, left 5. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5. So I've graphed both lines on the same graph. How many solutions am I going to have here?
Oh, sure.
1. How do you know that?
Because it's only crossing one.
Yeah, it's only crossing at one ordered pair. It's not the same line, and they're not parallel lines, correct? So if they just intersect at one point, that means that there is just one solution. So that's the first thing it wants me to do is determine the number of solutions that it has. It's got one solution. If it has one solution, which it does, determine its coordinates. So what's the ordered pair of our solution here? 2, 4, 5, comma,
4.
4.
2, 1.
Everyone okay with how we got that?
Yes, sir.
You go right 5, up 4 to get to that ordered pair that they're crossing at. So 5 comma 4 is my one solution of this system of equations. If I were to plug this into both equations, 4 in for my y's, 5 in for my x's, both of those would give me true statements. Okay? Any questions about that? How we feeling?
Awesome.
Graph the two lines on the same graph. Wherever they intersect, that's your solution. If they don't intersect, no solution. If it's the same line, infinitely many solutions.
Infinite.
Okay?
Oh, help me.
This is my last example here. Last example. Got to do the same thing here. Graph, determine the number of solutions. If it has one solution, tell what the coordinates are. Are these in slope-intercept form?
No.
Nope. So we've got to do that first off. Okay? So let's move negative 3x plus 2y equals 12 right here to give us some room to work it out. First step to get y by itself.
Add 3x.
Add 3x to both sides. That gives me 2y equals 3x plus 12. How do I get y by itself?
Divide 2.
Divide by 2. Divide everything by 2. Y equals 3 halves x plus 6. We okay with that first equation?
Yes, sir.
What's my slope here?
3 over 2.
3 over 2. And my y-intercept?
6.
6. So go up 6. On your y-axis, put a point. Positive 3 over positive 2. Which two directions, how many units am I going?
Up.
Up how many?
Up 3.
3.
Right 2.
Right, 2. Very good. 1, 2. That's going to be off my graph. So what other two directions could I go?
Down 3.
Down 3.
Oh,
Left 2 from our y-intercept. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2.
1, 2, 3, 1, 2.
1, 2, 3, 1, 2. Shh. Okay, that's all the points I can fit for that line. There's my first equation, graphed. Okay? Now, got to solve my second equation for y as well. What's the first step in doing that?
Minus 6x.
Subtract 6x from both sides. Gives me negative 4y equals negative 6x plus 8. How would I get y by itself now? Divide by negative 4. Negative 6 over negative 4 gives me what? Negative 6 over negative 4 gives me what? What was it reduced down to?
Oh, I got you. It's 4, 3. No, I'm lying.
What are 6 and 4 both divisible by?
2. It's 3, 2.
Positive 3 over positive 2x. 8 divided by negative 4?
4. Negative 4.
Negative 2.
Okay.
Okay. What's my slope here? 3 over 2. What's my y-intercept? Negative 2. Graph the y-intercept first. Down 2 on the y-axis. Put a point. Which two directions, how many units am I going? Positive 3 over positive 2.
Up 2, right. I mean, up 3, right here.
Up 3, right 2. 1, 2, 3, 1, 2.
1, 2, 3.
Shh. Stop. It's not necessary, y'all. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. Same thing. I can go down 3, left 2 to get more points. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. That's all the points I can fit for that line. There's my second equation. What do you notice about these two graphs, or these two lines? Parallel. They're never going to intersect. I knew that beforehand because they have the same slopes and they have different y-intercepts. So since these are parallel lines, how many solutions do we have?
No.
No solution.
Uh-oh.
That's all I got to write. That's all I want. Questions on example 6? How do we feel about solving systems of equations by graphing?
Yeah.
Feeling okay about it?
Sure.
There are 2 more methods to solve systems of equations by that we'll look at within the coming days. This is the first one, is solving by graphing. It might be one of the easier ones. Like I said, we'll look at the other 2 methods later on. Here's your assignment. 7.1, homework number 1, MH. That's what you're looking for on Canvas. Any questions about our notes before we end the recording?